So now what we're going to do is we're going to move on to those internal forces to figure out exactly what's going on. Now, fortunately, as we look at our two members here, we should notice that they are what are called two-force members. And so two-force members are members that are subjected to only two forces which are applied at the ends. So for equilibrium, the forces must be parallel to the axis between the force application points and equal in magnitude and in opposite directions. In other words, those two forces have to be applied along the line of action between the two endpoints, equal in opposite directions. And so you'll notice that I have these labeled as FAB and F'AB, two force members, so FAB and F'AB are going to be equivalent. Now what we have at this point is we have to figure out what those internal forces are. So how do we figure out what FBC and FAB are? So we've got a couple different ways of looking at it, and so you have method of joints and method of sections. I'm going to do the method of joints for this problem, but just a quick review of what the method of sections would be if this was our free body diagram. We have the 30 kilonewtons here. We have the forces, which I believe were 40 kilonewtons there, 40 kilonewtons there, and 30 kilonewtons upward. What we would do is, once again, it's in static equilibrium, so it doesn't matter where we do things. We would break the force right there, the structure right there, and then we would just tag the internal forces into the free body diagram. So we would have, FBC here, and then we would have FAB here, and then we would go and solve it just like we would solve it if it was a external force problem. What we're going to do is we're going to do the method of joints. And what is the method of joints? That is, you look at each individual point and you draw the free body diagram. So right here I have drawn, we have point B. And so I have all of my forces here. I'm going to have 30 kilonewtons pulling down. And then I have the internal forces of the member force AB, force BC. A couple different ways to solve this. One would just be to apply our standard equilibrium equations, some of the forces in the X, Y, and Z, and then solve the method of joints from there. Now, method of joints, we can't use some of the moments because there's going to be no moments about this individual point. We can use moments if we do the other method and do the method of sections. The nice thing about what we've got right here is we've got the three forces there. We can put this together as a triangle, just as shown here, looking at those three forces and how they do. And what's nice about that is we can use the law of sines. And when we have a triangle and we use the law of sines, how does that work? Well, it would be the force of AB divided by its length, and its length would be 4. So the magnitude over its length, we would have the force of BC over its length, which is 5. That's our hypotenuse here. And then we would have the 30 kilonewtons over its length, which is 3. And so this is using basically all the angles, and we could go and calculate out the angle. We could sit here using our 3, 4, 5 triangle, calculate out what theta is going to be. And in this case, theta is 36.87 degrees, and then we can just use the projections of the 30 kilonewtons on the FBC and FAB, or we can use the method of sines, which directly gives it to us. And since this is 3 quantities, they're all equal to each other, what I'm going to do is I can look at that one there, solve for BC, and then what I can do is I can look at this one is equal to this, and I can directly solve it for AB. And so if I go and do that, I'm going to find that FAB, the internal force in member AB, is going to be 40 kilonewtons. And then FBC, which is the internal force of BC, is 50 kilonewtons. And that's a big thing to remember, is these are internal forces. These are not external forces. We are not going to see this on the structure itself. We're going to see this inside each individual member. So if I go and I take any one of these little guys here, I know that I'm applying that force AB on it. If I cut it in the middle and get rid of, this side of it here, well, there is going to have to be an internal force in it that balances out of FAB. And once again, that's important. That's the key, because that is what we're going to use to calculate out what's going on. So that is the conclusion of our statics review, how to find out all of these external and internal forces. And from here, we're going to move on and start talking about states of stress.